I am Dr. Silvan, Assistant Professor, PG and Research Department of Biochemistry, St.Joseph College of Arts and Science, Autonomous, Cuddalore. I am going to present the measurement of radioactivity. Ziegler-Muller counter. The GM counter is an instrument used for measuring ionizing radiation. It detects ionizing radiations such as alpha particles, beta particles, and gamma radiation using the ionization effect product in the GM tube. GM molecules gets ionized when energetic particles, charged particles propagates through a gas. The electrons produced by ionization, if accelerated by a potential, can cause further ionization of particles, thereby generating a large number of more electrons. The instrumentation of GM counter, it consists of a hollow cylindrical gas tube. The GM Muller tube is filled with an inert gas such as helium, neon, or argon at low pressure, to which a high voltage, typically 400 to 600 volt, is applied. GM tube is enclosed in partially evacuated glass tube. A tungsten wire of 0.5 mm diameter is fixed along with the axis of GM tube. Tungsten wire is connected to a positive terminal. Metal GM tube is connected to a negative terminal of high tension battery. The diagrammatic representation for GM counter. The working principle of an GM counter: when an energetic particle enters the GM tube through a window, the gas molecules will interact with charged particles, it get ionized. The generated electron get accelerated towards the central anode and positive ions towards the cathode. The accelerated electron cause ionization of more gas molecules, generating a large number of electrons from a small interval of time is called avalanche. The avalanche gives rise to high current pulse for each particles enter into a tube. Successive current pulses are produced and counting is done by a suitable device. The readout device: there are two types of radiation readout. One is count, another one is radiation dose. Count: the count display is the simplest and is the number of ionizing events displayed either as a count rate, it's commonly counter per second, or as a total over a set time period. The count readout is normally used when alpha or beta particles are being detected. The second one, the radiation dose, it is displayed in a unit such as sievert, which is normally used for measuring gamma or X-ray dose rates. This graph shows the counter rate versus the applied voltage, the starting potential and then threshold potential and the operating potential. The approximately the voltage range is 300 volt, and then the breakdown potential. The lastly the continuous the discharge region. The applications of GM counter to detect radioactive rocks and minerals in the course of mineral prospecting, for fire responders, for making an initial determination of radiation risk, for hazard management personnel in checking for radiation danger in an emergency situation, to check for environmental levels of radioactivity near a nuclear power facility, to test for danger amidst a nuclear accident or leakage of radioactive coolant, to check for radioactive contamination of clothing and shoes in your workplace, radiation detection in the scrap metal processing business, to check possible leakage or exposure to X-rays in a medical facility, to check for radiation in areas where depleted uranium ammunition shells have been used. Scintillation counter. The formation of fluorescence due to excitation by radioactivity is called scintillation. The light emitted in scintillation can be detected by coupling into a photomultiplier. The photomultiplier, which converts the photon energy into an electrical pulse whose magnitude remains proportional to the energy of the original radioactive count. The instruments which measure scintillation are called as scintillation counters. There are two types of scintillation counters, namely solid or external scintillation counters. The another one, liquid or internal scintillation counters. Solid scintillation counting. The sample is placed close to a fluor crystals. The fluor crystals are zinc sulfate for alpha emitters, anthracene for beta emitters, sodium iodide for gamma emitters, which in turn is placed adjacent to a photomultiplier. This multiplier is connected to a high voltage supply and a scaler. Solid scintillation counting is useful for measurement of gamma emitting isotopes, but they are not useful for measuring weak beta emitting radioisotopes. Liquid scintillation counting are otherwise called as internal scintillation counting. The radioactive sample is dissolved or suspended in a scintillation system composed of solvent and primary and secondary scintillators. The radiation from the suspended sample molecules collides with a solvent molecules, imparting a discrete amount of its energy to the solvent molecules. The solvent molecule, which has become excited, the emit light as it becomes to a ground state. This process is called phosphorescence. The phosphorescence is due to the peculiar chemical nature of the solvent. The solvent emits light of a very short wavelength which falls in the range of 260 to 340 nanometer, which this range is too short to be detected by more existing instruments. A second molecule is known as primary fluor is added to the system. The compound absorbs light in a range of 260 to 340 nanometer and emits light of a longer wavelength. The longer wavelength light can be measured by most of the modern instruments. For instruments which are not capable of measuring this longer wavelength light, the another substance is called secondary fluor is added. The secondary fluor absorbs light emitted by the primary fluor and emit light with a maximum in a visible region. The photomultiplier converts the light energy into an identical signal that can be easily manipulated and measured. Autoradiography. Autoradiography is the bioanalytical technique used to visualize the distribution of radioactive labeled substance with radioisotope in a biological sample. It is a method by which a radioactive material can be localized within a particular tissue, cell organelles, or even biomolecules. It is a very sensitive technique and is being used in a wide variety of biological experiments. Autoradiography, although used to locate the radioactive substances, it can also be used for quantitative estimation by using densitometer. The autoradiography, the principle is imaging is the precipitation of silver atoms resulting from the ionization of silver halide by radio labeled samples. Silver halide is light sensitive compound commonly used in photography. They are generally suspended in a gelatin photographic emulsion. Each silver halide crystal molecule is individually encapsulated in a gelatin and functions as an independent detector of radioactive decay from the radio label sample. Once radioactive particles hit the gelatin emulsion, silver halide is reduced, resulting in the production of insoluble silver crystals. Gelatin photographic emulsions are used to coat photographic and X-ray films, which are made of a flexible base. When a radio label sample is in contact within a coated X-ray film, it generates a latent image corresponding to the radioactivity distributions within the sample. To make the image visible, the exposed photographic or the X-ray film must be submerged in a developing reagent, a chemical mixture that converts the silver crystals into metallic silver, darkening the gelatin emulsion. Silver nitrate is highly efficient in the reduction of silver halide molecules and is usually a component of developer solutions. The reactions in stopped by the fixative agent which removes the excess of silver halide from the photographic film. Highly radioactive areas produced more silver halide molecules, resulting in high optical density in the film.